Rima is one of the telescope operators who will be presenting what we do here in telescope operations. Essentially, I will start with saying that we have a 24-hour shift rotation to operate the telescope on site, which is in Cameroon, in the deserts. We have 3 shifts rotating in the day, non-stop operations. So essentially, it's 8-hour shifts per person. We have a team of about 11 people. We're rotating around the clock. Rima, you can take it from here.
Afternoon everyone, welcome to the operations team for radio astronomy. So basically we have a NECA telescope that we operate here. It's a telescope that's made up of individual antenna units, the one that you see there. So the idea is to combine 64 telescopes to form one huge telescope. The reason being, in the engineering wise will be limited because of structural deformations. So that's the reason why it's breaking down into single antenna dishes. So the way getting into the technical nitty-gritties, the way it works is that you will have a celestial source radiating radio frequency, and then once that radio frequency is gets into the telescope, it will first bounce off into the main reflector here. And from the main reflector, we have what we call a sub-reflector. So from the sub-reflector, we have multiple instruments that we use here, one being a receiver. So what a receiver does is that because those signals are very small in margin, what is that? It does is that it amplifies the signal into a huge format. And then the other thing is to clean up the noise. And then from the receiver, there's a second stage which we call digitization, where the signal will go from the receiver to the digitizer. The digitizer, what it simply does is to convert that signal from an analog signal into a digital signal that computers understand. Then from there, we have other machinery that are sitting in the Karun Array telescope on site. Once the signal gets digitized, it goes into another instrument which we call the correlator beamformer. So what a correlator beamformer does, because the signal will be arriving at these telescopes at different times, so it combines those signals and then form one signal. And what it does is that it corrects the phase of the signal and the amplitude in size and the time to make sure that they are all in time. So our duty as telescope operator, the main one is that we run observations, and the second one is to do control and monitoring, and then the third one is to troubleshoot, to solve problems that we might have that might arise as much as possible, and then to ensure that the telescope is optimized always. So the way in which we do that, we have a dedicated graphic user interface that we use, and then we access it through, there's a fiber link coming from site to here in the operations room. So firstly, starting off with first duty, doing observations, we liaise mostly with astronomers. So they will give us a schedule of what they would want to run throughout the day. And then we will prepare the telescopes, as you see in this first screen, where we have there's M0 until M63, means that those are the numbers of telescopes that we are using in the particular array. And then the other thing, once we started running observations, we check the signal quality, the power level. So this is the screen that we utilize to check the signal quality, to see that our power levels are corresponding from each and every antenna or receptor. And then there's also flag count, but that's coming to a part, the second objective that we do of monitoring. So there are subsystems that are very much critical to the telescope itself. meaning that if we lose that system, it means that we cannot operate for some time. So one of them being the correlator being wrong. It means that if it's off, then it means that our signals can be correlated. So it means that we are out, we can't operate until that is fixed. And then we have a dedicated screen that we monitor for that. Yeah. So the way that it's given to us, it's in alarm formats. So we will have green, which means if we see if it's a green alarm, then it means that it's functioning properly. And then yellow, it means that there's something that you need to look into. And then if it's red, then we know that there's a problem. Then we need to escalate it to the engineers or the maintenance people so that they can quickly resolve the issue. And then another critical system is time and reference frequency. We also look at alarms on that. It has 3 states of alarms, the red, yellow, the ones that I just explained. So what the TFR does is that it's also critical because it provides timely reference to the telescope, and then also it provides time to the digitizers. So if we lose it as well, it means that we cannot operate. So there's also one thing that's critical that we need to monitor. The screen over here shows the weather, meaning if our most culprit is wind, because if we have wind, it means that we cannot operate the telescope, because the telescopes are tracking, if they are in observation, they will be tracking whatever celestial source. So if we have wind acting in the opposite direction, it means that we are losing pointing accuracy, and then they can also damage the drives as well. And then lastly, there's a screen that we also look at over here, which is our sky coordinates. And then it has azimuth and elevation coordinates. And then we usually see the antennas, if they are clustered in the back, if they are tracking, they will usually move together in a cluster. So it means that if one antenna is not pointing, then we know that there's an issue with that. Then we also have a sightseeing where we can see the antennas on site over the camera. And then lastly, there's something that we also monitor, which is RFI, radio frequency interference. And then that's all in terms of control and monitoring. So the third objective, troubleshooting. We always try to minimize possible errors that we can solve on our operation site. If not, we escalate them to the maintenance team on site or the engineers. I think that's all in terms of operations.
If I may also add, you may wonder what these regular looking images are. We usually have aircrafts that land on site. On Wednesdays, which is our engineering day, engineers will go there to do maintenance work, and we specifically allocate the time for them to do the work. And we also want to see any other objects that we do not expect to see around the sky within the region that we are operating at. So we have a nice system here called Comrade. So what Comrade does, it shows us live what time the aircraft will be there. It even gives us the designation of the aircraft. If it's an SAA flight, we will see that SAA is flying over. We don't expect to be seeing SAA here. Why is it doing here? Right now I'm seeing SAA 343. We expect that to be happening. So for real, it's really there. So we are able to monitor. And this is important because when scientists collect the data, they want to be sure that they are not seeing things that they're not expecting to be seeing. For image quality, they don't want to be, maybe making reports that they're seeing an alien or transient object. Meanwhile, it's just something in the sky. So these are some of the things that we do. There are lots of other tools that we use to monitor and to do the debugging and fix the system itself. What else? We actually have some of the power supply monitoring tools here. As you know, as South Africans, you would know that we have a very big problem with ESCOM. So we have a diesel generator on site. It's actually operated with router machines. So whenever there's a power failure, we are able to see over here, and we need to monitor that to ensure that the system continues to run. And should there be a problem, for instance, diesel is running out, that engineers or technicians on site can quickly run and refill, and then we can carry on running. So those are some of the things that we have. There's actually a number of other displays that we have that we are able to look into and observe. In terms,
can I also say something?
Yes, please. By the way, Audrey.
No, they know me already.
Oh, they do know you.
Do you guys see these yellow colors here? These yellow colors are flags. So the reason I'm talking about them is because there's a reason why we're in the Northern Cape where we are at that semi-desert place, right? No traffic in terms of people, cars, cell phones, fridges, petrol cars, and so forth. Because those things cause what he said is RFI. Let me give you an example of what RFI is. You're watching TV and then your cell phone's about to ring. What happens to the screen? You're in the car and your cell phone's about to ring. What happens to the signal on that radio? In here, it's different in that everything will be flagged. If there's a cell phone there, all the data that's been taken will be flagged, and therefore it's useless. So whatever data was taken, no matter how big the file is, if there was a cell phone signal or a radio signal, Bluetooth, your laptop, it's not on flight mode, microwaves, TV, then all the data will be lost. And obviously, every minute is money. And we have to account for that. So every Friday they have operations meeting where they discuss all the problems that are on the system, how they fix them, what can they fix, where should engineers intervene. But there's always accountability to the loss of the system.
That's why I told her earlier on that she must come and visit.
Never. Alright, let's go back to SAO.
So your social means, you guys
Yeah, I think
any questions?
Do you guys have questions? Yeah, I think we can ship over to SAO now. Alright, thank you, Kenya.
Thank you.